Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams,
and I am Gary James.
And we'll be working together for the first time in almost a year. The COVID-19 pandemic had been keeping us both pretty much close to home.
The subject of this presentation is the scientific calculator, a truly disruptive technological development that devastated a long-established industry. The slide's origins,
slide rules
origins go back to the 17th century. You could always tell the engineering students on campus because they were the ones carrying slide rules. The high-end slide rules came with carrying cases you could clip to your belt.
Yeah.
Oh, how cool.
Yeah, right. Nothing says nerd like slide rule clip to your belt.
And if these engineers were freshmen, you could spot them a mile away by their T-squares and tackle boxes of drafting supplies. The slide rule was an analog computer chiefly used for multiplication and division. This was accomplished by addition and subtraction of logarithms. Slide rules usually had other scales that could be used for other purposes, like taking square roots and finding trigonometric functions. The slide rule was the standard personal computing device for engineers and scientists until the early 1970s.
And then?
The photo shows a post-slide rule from the late 1940s that belonged to Dave's dad, and a Texas Instruments SR50 scientific calculator. The introduction of the scientific calculator caused the slide rule business to collapse, and long-established companies like Post and K&E left the business.
Within a year, the whole thing was gone. Now, this is an example of the Hewlett-Packard HP35. This was the world's first scientific calculator, and it was introduced in 1972. Now, this calculator, this particular photo, was taken in July of 2021. The calculator is still functional after, it's been close to 50 years. The display is showing the tangent of 60 degrees. Let me explain here. The HP35 was named that because it had 35 keys. There's the LED display, an on-off switch, that's CHS, or change sign key, that would change the sign of the operand that was showing on the LED display. There's the enter key. These are the basic mathematic function keys: add, subtract, divide, multiply. There's a clear key for clearing entries. EEX was for entering scientific notation. CLX was to clear the X register. I'll explain shortly what the X register meant. These were the numeric keys, which included a dedicated pi key.
We will shortly show some basic operations of the register stack of the HP35, but first let's go through some of its commands.
Jump the gun here, okay.
This is the exponential key, the log base E key, the log base 10 key, X raised to Y power key, the square root key, reciprocal key, trig function and inverse trig functions. We're in this bank. The recall key, the store key, row registers key, exchange X and Y. Now, the computational capabilities of the HP35 were evident.
I mean, you just look at all the functions that were available on this particular calculator's keyboard. Just amazing.
So the original selling price was $495 in 1972.
And that was the time when my dad, as a mechanical engineer, was earning about $1,000 a month, by the way.
Mhm. This particular HP 35 was acquired in 1975 for 75 bucks.
Because I remember acquiring it for my older brother.
HP had ceased production and was selling off their inventory. This particular unit was a manufacturing defect.
Or has a
manufacturing
yeah.
defect, yeah.
Okay.
Which is revealed it has two EEX keys and no CLX key.
In other words, it had two keys for scientific notation, but no clear the X register. Somebody put the wrong key in the keyboard when it was manufactured. The unit works fine, but the wrong key was in there. So there you go.
Okay, so this is where the extra EEX key appeared.
Yep. We found
okay,
the unit
yeah, this unit was discovered circa 2008. Had been unused for a number of years. The charger was missing and the batteries had become unusable long ago. The unit shown operating from an external DC source, right, which they happen to provide for us.
Yeah, well, yeah, okay. So let me talk a little about the HP register stack and its basic operations. The HP 35 had 4 registers, which were known as the X, Y, Z, and T registers. And the number that was shown on the display was the number that was in the X register. The exchange register key, which looked like X to Y, Y to X, it would take the contents of the X and Y registers and swap them. It could be useful for changing the order of operands, if need be, for like say division or exponentiation. But it just affected the contents of the X and Y registers. Then there was this rotation through registers key, the R with a down arrow that Gary mentioned. Or did I mention that?
I think you mentioned.
I mentioned that. Short-term memory is just gone. Anyway, and if you roll through the registers, the register stack would drop by 1, T to Z, Z to Y, Y to Z, but the contents of the X register would be copied to the T register. So it made a circular buffer, and you could cycle through the registers. Okay, now let me show you some examples of how you did operations in the HP 35. A unary operation, one that only involved one operand, like a square root, for example, or an exponential or a logarithm. You would key the argument into the X register. Like in this case, you key in 31, and then you hit the square root key, and the answer appears in the X register, the square root of 31. Simple. Now, let's talk a little about how you did a binary operation. So let's take 5, and then we hit the enter key, and you see what it does is it copies the X register to the Y register. So you've got 2 copies there. You have 5 in both places, but now you can overwrite the X register by keying in another operand. And then if you hit multiply, the X and Y values are multiplied and the result goes into the X register. Now, if let's say that I want to add 3 to that, I would key in 3 plus, and the answer is 23. Let's look at a sequential operation using binary operations, using all of the stack registers. So let's enter a 5, or key in a 5 and hit enter. Now we have the 5 in both X and Y registers. Now let's enter a 4. We're going to type a 4 and then hit the enter key. And you see each time you hit the enter key, it raises the stack. And what was in the X register is copied to Y. What's in Y is copied to Z. What was in Z is copied to T. And now let's add a 3. We'll overwrite the 4 with a 3. And then we'll hit enter again. That raises the stack one more time. And then let's enter a 2. And you see we've now got 4 different operands stored in these registers. And now look at this. Multiply. and that takes these two registers and multiplies them. The result is written to the X register, the 6, and then the stack drops. But as the stack drops, the T register is copied down to the Z. Now, if I hit plus, the X and Y registers are added. Result goes to the X register. The stack drops, copying down. And finally, I can hit divide, and that takes 5 in the Y register and divides it by 10 in the X register, and the result is 1/2. And you notice there's no parentheses here, no use of an equal sign. The second and third examples here are illustrations of the Hewlett-Packard 35's use of what was known as Polish postfix mathematical notation, which was also called reverse Polish notation, or RPN, which was first described by Polish logician Jan Lukowicz in 1924. RPN is more efficient than what is known as infix notation, that is putting the operator between the operands, and requires no parentheses to evaluate an expression as long as each operation has a fixed number of operands. And RPN was a unique feature of the Hewlett-Packard calculators. Now, I wondered about how did these calculators do these mysterious functions? How did they do these impressive things like exponentiation and taking cosines and sines and so forth by push of a button, things you used to have to, like look up in the math tables? How do they do that? And certainly couldn't be by a lookup function. It'd take far too much memory. So I did a little digging into Hewlett-Packard 35's methods of calculation. I found an HP journal from 1973 that described the so-called CORDIC method used for computation of trigonometric functions. And I think it's worth spending a few moments to look at. So the basic principle behind the CORDIC method, and to be quite honest, the CORDIC is an acronym and I don't know what it means. Oh, well.
There you go.
Yep. Anyway, can't know everything. It's based on the idea of this rotation matrix. Let's take an original vector, which we call x naught and y naught. These are the x and y coordinates of a vector. And we're going to take that vector, which extends from the origin 0, 0 to x naught, y naught, and we're going to rotate it through an angle of gamma degrees. And that's going to produce two new points, x1 and y1. Now, I can take this matrix and I can resolve it into two independent scalar equations that tell us x1 is cosine gamma times x naught minus sine gamma y naught, and y1 is sine gamma x naught plus cosine gamma y naught. Now, if I want to normalize the diagonal coefficients of this rotation matrix, and there's a reason for that, which I think will become maybe evident in the next slide, but I could simply multiply everything here by cosine of gamma, which would then change these terms inside the matrix to sine gamma and minus sine gamma, which would be then replaced by sine over cosine, which would make the tangent. So 1 on the diagonal, and tangent gamma and minus tangent gamma in the off diagonal elements, multiply the whole thing by cosine of gamma. And then if I want to, there's a useful trigonometric identity. The cosine of gamma is 1 over the square root of 1 plus tangent squared of gamma. So all I really need to know here through this calculation is the tangent of the angle. And so then I can write the matrix equations for rotation of a vector in this form. Now, let's assume that this original vector is a unit length vector that's at an original angle theta. So then the elements of the original vector here become the cosine and sine of that angle. So graphically, what we're doing is this. We're taking an original vector at an angle of theta and a length of 1 out to a unit circle, and we're rotating it through an additional angle gamma to produce a new vector at theta plus gamma. So this expression above gives us the new coordinates of the endpoint of the vector drawn from the origin to the unit circle at an angle of theta plus gamma. Confused yet?
Somewhat.
Somewhat. Okay. Well, let's just show how this works. Okay. So let's assume that we want to find the trig properties, the sine, cosine, and tangent of, say, 72 degrees. Okay. And what we'll do is we'll start with a unit vector at 0 degrees, which has coordinates of 1 and 0. And we'll rotate it by 45 degrees. Why 45 degrees? Because the tangent of 45 degrees is 1. So I know what the rotation matrix is for 45 degrees. Okay. Now, if I rotate that new vector at 45 degrees to another 45 degrees, I go to 90 and I go past my original argument of 72 degrees. So I can only rotate once by that method. But now let's suppose that I continue rotating by successive rotations. I drop the tangent from 1 to 1/10. And the inverse tangent of 1/10 is 5.7106 degrees. So I can start at 45 degrees and rotate by 5.7106, the second rotation. The third one, I'm starting at 50.7106 and rotating another 5.7106. Then here's the fourth rotation, starting at 56.4214 and rotating through 5.7106. And here's the fifth rotation. And I now start at 62.1318 and rotate through 5.716. And if I try to do it again, rotating through 5.7106, I'll go past 72 degrees. So I want to cut the size of my increments. So what do you think I would do?
I would say you are now going to change it by another factor of 10 and start rotating by 0.01.
Yeah, by the angle whose tangent is 0.01, yes. Drop that by a decade, and that's 5.7294 degrees. And so I carry out successive rotations by 5.7294 degrees until I get so close to alpha that I can't do it again. And then if I want to, I can go to, what do you think would be next?
The next degree, which would be
our tangent of, our tangent of 0.001, yes, and I can continue on like that. And eventually I will wind up with a final vector whose coordinates are, whose x value is the cosine of 72 degrees and whose y value is the sine of 72 degrees. And if I want the tangent, I divide the sine by the cosine, and there we are. So that was how they did it. Okay. Now, I was also curious about some other functions. So I was doing a little digging. I could not find anything that really said that this was the algorithm used for computation of square roots in the HP35. No disclaimer there. But this is a method that could have been used. It could have been programmed into the HP35. So with that caveat, let us proceed how they might have done a power series computation for the square root of x.
Okay.
Now, you can calculate a power series using a Taylor series or a Maclaurin series. A Maclaurin series is a Taylor series where the point of expansion is around 0. And the basic Maclaurin series says that the function, some function evaluated argument x is the function evaluated at 0 plus the first derivative of that function evaluated at 0 multiplied by x plus 1 over 2 factorial times the second derivative evaluated at 0 multiplied by x squared plus 1 over 3 factorial, third derivative x cubed. And the
I see a pattern.
Yes, here. This is a power series. And you know, if you're in your first year of calculus classes, or I think maybe even in analytic geometry, they teach this. So anyway, you're familiar with this stuff. Okay. The problem, though, for square root is the Maclaurin series won't work because the derivatives of the square root of x are not defined at x equals 0. But we can use an artful dodge here. Let's use f of x as the square root of 1 plus x. Now, the derivatives of the square root of 1 plus x do exist for x equals 0. And so the derivative, first derivative of square root of 1 plus x at x equals 0 is 1/2. The second derivative is minus 1/4. The third is 3/8. The fourth is minus 15/16. The fifth derivative is 105 over 32. And the sixth is minus 945 over 64. And the pattern keeps continuing. It's easy. These are easy to calculate. Okay, so using these values for the derivatives evaluated 0, it produces a Maclaurin power series for the square root of 1 plus x with a region of convergence of the absolute value of x is less than 1. Well, obviously, this is of limited usefulness to us because, say, for example, that we wanted to calculate the square root of 10, then we would use x into our square root of 1.10 is 9 to calculate the square root of 10. But if the region of convergence is absolute value of x is less than 1, I can't do that. So, however, we are clever because we are engineers. Actually, I'm an engineer, but we are both ham radio operators. And
that makes the difference.
Yes, we are clever. So let's keep going. So let's extend this method to arbitrary positive arguments. And let's show this numerically by showing the square root of 192. Let's first determine a number which is the smallest even power of 2 that's greater than the argument of the square root function. So what is the smallest even power of 2 greater than 192? That would be 256, which is 2 to the 8th. Why even power? That'll become evident in a moment. So let's compute 192 as 256 minus 64, which we can also write as 256 times 1 minus 64 over 256, which conveniently turns out to be 256 times 1 minus 0.25. Now, we're in a position to find the square root of 192. It's the square root of 256, easy to find, times the square root of 1 minus 0.2500. Now, the square root of an even power of 2 is easily computed by bit shifting. And the new argument of 1 minus 0.25 fits the pattern of 1 plus x with x equals minus 0.25, which falls within the region of convergence of the power series. And straightforward computation with the of the Maclaurin power series with the coefficients we've already determined, and x equals minus 0.25 out to 13 terms, and multiplication by the square root of 256, which is 16, gives us the square root of 192 is 13.856406. Now, let me put my disclaimer in here again. This is an example of a power series method for computing square roots. I'm not making a claim that this was the actual method embedded in the HP35, but I would guess that what's behind the square root key in the HP35 is probably very close to this.
Something similar.
Right. Okay.
Now let's look at Texas Instruments' first scientific calculator, the SR50. This particular calculator was photographed in July 2021.
And it is also displaying, by the way, the tangent of 60 degrees. Okay.
SR stood for slide rule.
Yep. They were still thinking of slide rules in those days.
The original selling price of $170 considered less than the HP35 price reduction in 1973 to $395.
Yeah, and what it was down to in 1974 when the SR50 was introduced, I don't know, but still the HP35, when I acquired my first HP35, it was $395.
Mm-hmm.
Okay.
This is the LED display. This is the degrees and radian switch. Trig functions resided here.
Okay.
The HYP key for hyperbolic trigonometric functions. unary functions,
Yeah, ones that take only one argument, like square root, factorial, reciprocal.
the store and recall keys, and the numeric keypad.
And I should point out here that the change sign key on the HP35 is handled here. This was to change the sign of the operand key.
Yes. Okay, this is the on-off switch. This is the clear key. This is the X root of Y key. Y raised to X key. And these are the math functions.
Basic add, subtract,
multiplication, divide, yes. And this is the equal key, something we're all familiar with on a calculator.
Mm-hmm. Unless you used HP, but okay.
Yes. Let's continue looking at the SR50. This is the logarithms and exponentiation key, or area.
Keys, yes.
Yeah. Degree and radian conversion key, summation key, clear entry key, scientific notation, on-off switch, clear key, exchange X and Y registers key. This is the dedicated pi key. The SR50 expanded on the functions and capabilities of the HP35. The SR50 included calculation of factorials, the ability to use either radians or degrees, and computation of hyperbolic trig functions and inverse hyperbolic trig functions. But for many engineers, these extra capabilities were not important.
Not terribly.
Unary functions, those with only one operand on the SR50 were the same as the HP35. Key in the number, press the function key, and that was about it.
And that was it. Simple.
Binary functions with two operands use so-called infix notation, also known as algebraic entry. In this notation, the function appears between the operands. Example, adding 3 to 6 takes these steps. Press the 3 key, the plus key, the 6 key, and the equal key. And the result 9 appears on the display. Computations with infix notation usually require more keystrokes than with RPN, but the advantage of RPN is not large. Which you chose was largely a matter of personal preference. Hewlett-Packard's use of RPN was turned into a clever advertising slogan which said, "Our calculators have no equal." Whoa.
I remember that.
Okay. These are 3 NiCad batteries gave an operating voltage of 3.6 volts. The top picture shows the batteries for the HP35 in their plastic cradle. These replacement NiCad batteries are not the originals.
From 1975.
Correct. The bottom image is the original battery pack from the SR50 removed from the calculator in 2021.
Yeah, so those batteries are 40 plus years old, long since ceased to work.
Yes. 3 NiCad batteries gave an operating voltage of 3.6 volts.
Yeah, right.
NiCads were rechargeable and had low internal resistance necessary to supply the current required for LED displays. But they suffered from a so-called memory effect.
We will have that these days.
Yes, we do. And were subject to internal short circuiting, so do I, if left uncharged over a long term.
When was the last time you were charged?
It's been a while.
It's been a while, yes. Well, and one other thing I should mention about these NiCad batteries. NiCad batteries have a discharge characteristic where they hold their cell voltage until they're virtually exhausted. The voltage does not drop much at all until the battery is virtually completely discharged. And so what could happen was, as your batteries were running out, like on the HP35, as the batteries were starting to go, all of the decimal points in the display would come on to tell you the battery is about shot. You had only a couple of minutes of operating time left when all the decimal points came on. I don't remember if the SR50 had a low battery indicator. I don't. See, my weapon of choice back in those days was the HP35. And the SR50 was my dad's weapon of choice to replace his slide rule. But okay, whatever. So to operate these calculators here, do a live demo of them, we are using a homemade 3.6 volt DC regulated supply. It uses a low dropout voltage regulator, a linear voltage regulator, and 4 AA batteries. And we have a 2.5 millimeter plug that delivers power to the SR50 through its, what was its charging port. And we've made a 3-pin custom plug that connects to the HP35 charging port. And now what we're going to do, to give us a brief moment to reset things, we are going to show some live demonstration of the SR50 and the HP35 and show that almost 50 years later, these antiques are still working. Okay, give us a moment and we'll be right back. So here's the HP35 in its original carrying case. Gary, you want to unzip it and take it out?
Let's reveal this gem.
Reveal this gem, yes, here you go. And there is, ta-da, an HP35 seeing the light of day after almost a half a century. So here we have the HP35. And let's show a couple of unary functions first. So why don't you key in 3 and then hit the exponential, that's e to the x key. And there we have a result of 20.0855 and so many digits. Okay, that's cool. Now let's show the square root function. Why don't you key in, let's say 256. 256, and then hit the square root key, and that should give us 16. Yep, there we are. Now let's show that stack at work. Okay, do something a little more complex. Hit 5, enter. Enter, this is the big broad key right there. Yep, enter key. 4, enter. 3, enter. 2. Now we've got all 4 operands stored in the stack. Hit multiply. That will multiply the X and Y registers and gives us a result of 6. Now press add. That's 10. And now press divide. Now give us Y divided by X. And there is the answer of 1/2. Now that particular, entering that particular expression required 10 entry operations on the HP35. And now we'll do a quick demo of the SR50. And this is the SR50 in its carrying case. Gary, you want to reveal this oldie but goodie to the world?
Ta-da! Ta-da. Here we come.
Yep, there is the SR50. And just for the record, why don't you turn it around so you can show the label that's on the top side of it. Yep, this was my dad's calculator that he used in the 1970s. Okay, so we will tell you what. Why don't you just connect it up to the power supply?
Okay.
It's that 2.5 millimeter plug. It just plugs into the charger port, and there we go.
All right, now we're powered up.
On the air. Okay, so let's let's demonstrate here. Let's show a unary operation. In this case, let's do the factorial, which was a built-in function on the SR50 that wasn't available in the SR35. Factorial is one of the x followed by exclamation point. Let's do a factorial. Let's do 6 factorial. 6, and it's 120. Okay. Yeah, you remember what factorial was? That was factorial of x is x times x minus 1 times x minus 2 minus x minus 3, etc. And the factorial of 0 is defined as 1. So yeah, okay. Now let's try something here. Let's key in like 999 and now hit factorial.
Whoa.
Yeah, you see that? It blinks all 9s to the 99th power. That was how the SR50 lets you know that you had done an illegal operation.
Does not compute.
Does not compute. Does not compute. No, and this was, I forgot to ask you to demonstrate an illegal operation on the HP 35, but it would put up a similar all 9s display to let you know that you had
gone out of bounds on this calculator.
Okay, so hit the clear key. Let's clear that. And let's try that same algebraic entry that we did to compute, that we just computed with the HP 35. So, well,
yes.
Okay.
I think Mother Nature is waking up.
Hazards of live recording. Okay, 3 times 2 equals plus 4 equals 5 divide. Now swap x and y, the XY key equals. And we did something wrong.
Yes.
Okay, let's try this again.
Okay,
so let's clear everything.
Buffer.
3 times 2 equals plus 4 equals, okay, 5, or divide by 10. Oh, you know what? I did it wrong again.
I think you did.
What is
swap?
Yeah, okay.
XY.
Okay.
Okay.
Oh my goodness.
We're showing.
Do we want to try this one more time?
Yeah, sure we do.
Okay.
Yeah. We're just showing.
Trying to show the computation of the same expression on the SR50 as we just did on the HP 35. All right. So 3 times 2 equals. Okay, that's 6. Now add 4 to that. Plus 4 equals. Now what we want to do is divide 5 by that number. So now key in divide. That was the mistake I was making. 5. But now if we go ahead and do that division, it will be 10 divided by 5. And we wanted the operands in the opposite order. So let's do the XY. And now equals. There we go, finally. And we got 1/2. Now, this expression required 12 key entry operations on the SR50. So as I pointed out earlier, the reverse Polish notation was more efficient, fewer keystrokes needed to enter an expression into the calculator. But it required a little getting used to, although the current learning curve was not that steep. I actually preferred reverse Polish.
I was going to say, and once again, it was personal choice, correct? Yeah. Either one.
You could do it either way, but I learned on the HP 35 and I came to prefer the HP 35 in reverse Polish notation. I've continued to use Hewlett-Packard calculators since then. But anyway, the SR50, though, did implement some functions that were not available on the 35, like factorials and trigonometric cosine functions and inverse, I can't believe I said that, hyperbolic trigonometric functions. Oh my. And which the HP35, you could calculate them with an HP35 from the definitions, like cosh of x, hyperbolic cosine of x, is e to the x plus e to the minus x entire thing divided by 2. But you could do that with the push of one button on the HP.
Yeah.
I mean, on the Texas Instruments SR50. However, very seldom in my professional career did I ever have to calculate the hyperbolic cosine of anything. So I like RPM.
Okay.
Okay, so now that we fumbled our way through this thing, let's put a wrap on this.
All right.
Well, I hope you enjoyed our little demonstration of these important calculators from
Or blast from the
the
past.
blast from the past.
We appreciate your visiting the past with us.
And look for this next time.